Hi guys, this lesson is about optimization. This is section 3.7. So let's start with a few problems. Let's look at the first one. We want to find two positive numbers that satisfy the set of given requirements. In part A, we are looking at having the product of 185 and we want to minimize the sum. So let's look at how we're going to solve this. So we want the product to be 185. We don't know what the numbers are, so let's just call them x and y. So we want x times y to be 185, and we want to minimize the sum in some way. And our sum is going to be x plus y. These problems, every one of them, will either be a minimizing or a maximizing problem, and they almost always require some kind of substitution. In this case, we can take that product equation that we have and we can make a substitution into the equation we're trying to minimize or maximize. So if we were to solve this equation for either x or y, and it doesn't matter which one you solve for, I'm going to solve it for y. And I can do that by dividing both sides by x. So we can substitute into the sum equation. So now our sum is equal to x plus 185 over x. And we can rewrite that. Now, anytime we want to minimize or maximize, those are keywords to let us know we need to take a derivative. So if we take the derivative of s, and I'm going to use that notation. So now we have the derivative, and we need to set this derivative equal to 0 and find critical numbers. So we're going to move this term to the other side by adding. So 1 equals 185 over x squared. We're going to multiply both sides by x squared. And then we're going to take the square root of both sides. So x equals plus or minus square root of 185. Now we want positive numbers, not negative, so we're going to only consider the positive 185 square root value. Usually you want to confirm that this is going to be a minimum, and we can use that sign chart to help us do that. If we were to look at the first derivative and create our sign chart with the square root of 185 on there, let's plug in something to the left of 185 like 0. So if we plug 0, well, 0 is probably not a good number since we're dividing by x squared. Let's substitute in a 1. If we were to substitute 1 in there, we're going to end up with a negative number. If we substitute anything bigger than the square root of 85 in here, we're going to end up with a positive number. So that tells us that this function is decreasing then increasing. So if it's decreasing then increasing, then we know we have a minimum value. So this has definitely got to be our answer. To find y, we're using that substitution that we had earlier where we said y was equal to 185 divided by x. So we have 185 divided by the square root of 185, which ends up being the square root of 185. So our two numbers are x equals square root of 185 and y equals square root of 185. Let's look at the second problem. In part B, they're telling us the sum of the first number and twice the second number is 108, but now we want to maximize the product. And this is part 1B. So let's come up with an equation. If we take x plus 2y, we know that sum has to be 108. That's the sum of a number plus twice a second number. And we want to maximize the product, which is x times y. Now, just like before, we're going to have to make a substitution. So this equation would be easy to solve for x. If we move that 2y over, we now have a substitution we can use in here. So p is equal to x, which is 108 minus 2y, times y. If we distribute, we end up with a 108y minus 2y squared. And now we want to take the derivative. Remember, we want to maximize, and maximize is a key word to let us know we want to take a derivative. If we take the derivative of this, we have p prime is equal to 108 minus 4y. And if we set that equal to 0, we can solve for y by moving the 4y over and then dividing everything by 4. So y is equal to 27. And now that we know y, we can substitute back in to find x. We know x is equal to 108 minus 2y, which is going to be 108 minus 2 times 27, which is going to be 54. So there's our solution. If we wanted to confirm that this was going to be a maximum, I'm backtracking just a second here, we can go back and do that first derivative sign chart. If we were to put 27 on here, which is our critical number, we could substitute numbers to the left and to the right into the derivative. So if we were to plug in 0, we would get a positive. If we would to plug in something bigger than 27, like 30, we would end up with a negative. So this confirms that the function is increasing then decreasing, which means we have to have a maximum value. So the sign chart's just a good way to confirm whether or not you're on the right track. Let's look at another problem. Number 2, we have an open box of a maximum volume that we're making from a square piece of material, 24 inches on each side. And we're cutting equal squares from the corners and turning up the sides. We want to write the volume as a function of x, and then we want to maximize the volume. This is one of my favorite problems, by the way. So let's look at how to tackle this. I like to start by drawing a picture. So here's our square. This is 24 inches by 24 inches. And we are cutting out corners. So we're going to cut these 4 corners out. And that will allow us to fold up this side, this side, this side, and this side. And we'll be able to create a box. Now, we don't know how big of a corner we want to cut out. So we're just going to call it X. So if this was originally 24 inches and we cut out a piece here that's of length X and a piece here that's of length X, then this new length is now 24 minus 2X. It would be originally 24, and then we're taking this piece off and taking this piece off. This side would be the exact same way. So we would cut this piece off and this piece off, which would also be 24 minus 2X. That's going to leave us with a box. It's not going to have a top. It's going to be an open box. And we need to find the volume equation. We know volume is length times width times height. So in this case, the length is 24 minus 2X. The width is 24 minus 2X. And the height of this box will be X. And we can write this a little more concisely if we write it this way. Now, this is a cubic equation. Usually cubics don't have any kind of restrictions, but because this is a real-life example, optimization is all about real-life examples, there are going to be some domain restrictions on this. We can't cut out a piece of the side here that has a length smaller than 0. So there's a lower bound for the domain. Also, if we're looking at this side, the biggest we could cut out is of length 12 for x, because if we cut out 12, then 24 minus 2 times 12 would be 0, which means we wouldn't have a side here. The whole piece would be gone. Okay, so notice we're using the inequality less than here. It's a strictly less than. We can't include the 0. We can't include the 12. Now we have a volume equation. Let's take a derivative. And I'm going to take the derivative using the product rule and the chain rule. The other option would be to multiply everything out and then take the derivative that way. But we're going to want to set this equal to 0, and it's going to be easier to do that if we take the derivative using product rule and chain rule. Product rule says it's the first one times the derivative of the second. Don't forget to take the derivative of the inside, plus the second one times the derivative of the first. So there's my first function x, here's my second function. So I'm going to clean this up just a little bit. I have a 2x times a negative 2x, which is a negative 4x squared, times 24 minus 2x, plus 24 minus 2x squared. Okay, both of these groups have a 24 minus 2x in common. That's going to leave us with a negative 4x plus 24 minus 2x. So we have 24 minus 2x times 24 minus 6x. So let's set this guy equal to 0. And when we do, we have 24 minus 2x is equal to 0. So we have a critical number at 12. And then 24 minus 6x is equal to 0. So we have another critical number at 4. Now, 12 is outside of our domain. So 4 is our winner here. We can confirm that by looking at the first derivative sign chart. Remember, we can't go below 0. We can't go above 12 because of domain restrictions that are implied. So if we were to take that derivative and substitute something in between 0 and 4, like 1. If we plug that in here, we're going to end up with 24 minus 2, which is a positive, and then 24 minus 6, which is a positive. If we substitute something in bigger than 4, like 5, we would have 24 minus 10, which is a positive. And then 24 minus 30 would be a negative, so we would have a negative. So you can confirm that this is definitely going to give us a maximum value. So now let's go back and look at our dimensions. We know x has to be 4, so that's going to be the height of this box. The length is 24 minus 2x, which is 24 minus 2 times 4, which is 16. And the width happens to be the same thing in this case, since our width was also 24 minus 2x. Remember, we were creating our box from a square to begin with. So the dimensions, it's 4 by 16 by 16. And if we multiply that together, we will get the maximum volume that can be created from this box, from this piece of cardboard rather, which is 1024 inches squared.